Well, good evening and welcome to a very, very special Jeffrey B. Graham Perspectives on Ocean Science lecture this evening. My name is Nigella Hilgarth and I'm the Executive Director here at the Birch Aquarium at Scripps Institution of Oceanography. And it is my great pleasure tonight to introduce our speaker, who is familiar to many of you and a great friend of many of you. Dr. Charles Kennel was born in Cambridge, Massachusetts, and he received his bachelor's degree in astronomy from Harvard and a doctorate in astrophysics from Princeton University. And before joining Scripps, Dr. Kennel spent nearly 30 years at UCLA as a professor of physics and ultimately executive vice chancellor. And he's the author and co-author of more than 250 experimental and theoretical publications. So a highly distinguished career in academics and in administration. He was also an associate administrator for NASA, directing Mission to Planet Earth, which is the world's largest Earth science program ever. And as many of you here tonight know, he was also the 9th director of Scripps Institution of Oceanography and the vice chancellor of marine sciences for UC San Diego from 1998 to 2006. And he is presently distinguished professor of atmospheric science at Scripps Institution of Oceanography here in UC San Diego. And he is the founding director of the UCSD Environment and Sustainability Initiative, known as ESI, which is an all-campus effort embracing teaching, research, campus operations, and public outreach. And he is now the chairman of ESI's International Advisory Board. And so there is really no one better to speak to us tonight on work that he did when he was on sabbatical. And he did part of that work on sabbatical in England's green and pleasant land, and many of you will not be surprised to learn that I'm familiar with that country. So please join me tonight in welcoming Dr. Charles Kennel, who will be speaking on science solutions for a planet in peril. Charles.
Well, thank you very much, Nigella. I look out and I see quite a number of old friends and colleagues and some new friends, and I just want to thank you all now for coming out on a night that threatens to be rather rainy and perhaps unpleasant when you leave. So it's by just a great good accident that this happens to be the one-year anniversary of the first lecture that I gave at Cambridge, which was the lecture named in the honor of C.P. Snow at Christ College, where I was a visitor. So I thought I'd spend a little time and tell you who C.P. Snow was. Actually, C.P. Snow is the person that introduced the idea into modern academic thought that there was a real cultural divide in our universities and subsequently in later life between the scientists on the one hand and the social scientists on the other. And that it was this split between the two cultures that made his life in public policy exceptionally difficult to deal with. In 1959, he gave the famous Reed Lectures, which were the oldest lecture series in Cambridge, founded in 1519, in which he introduced the idea of the two cultures in the scientific revolution. And it happened thereafter that he traveled to Harvard, where I was an undergraduate, and I attended a similar lecture at Sanders Theater. Now, at that time, I was young, and I was having trouble grappling with a single culture. And the idea that there were two was almost intolerable. And I put the thought away for many, many years, but now, almost 50 years later, I begin to see what he meant. And I might, in fact, for the first time, have something pertinent to add to his discussion based on my life's experience. So my topic, however, will be to discuss this whole issue between the two cultures in the context of the subjects that I have been working on for the last 15 years, and is a major preoccupation, obviously, of the Scripps Institution of Oceanography. So I'm going to call this global Earth science and point out that our global Earth science is going to be challenged by the demands of sustainability. I'll tell you a little bit about what these demands are. I'm going to focus on the passage of time, the last 50 years, the next 50. I'll try to explain a little bit about how we are gradually evolving towards a sustainability science, tell you a little bit about Earth system science, finally have a plea that in our own field we can see the cost of the split between the natural and social sciences, and we've got to bridge the two cultures before it's too late. But let me start at the beginning. Our civilization faces an entirely new circumstance. This is a picture that has been devised to give you an idea of where people are undertaking combustion that is affecting the atmosphere. The red is biomass burning. The yellow is underground peat bogs. The blue, believe it or not, is offshore operations where carbon dioxide is being generated. And the white is our electrical civilization, all our electric lights shining up into the sky. So now you can see where the people are, where our activities are, and where our energy, our civilization's energy is being generated. Now, people have altered their environment to suit their needs from the very beginning, certainly from the beginning of the Industrial Revolution. So what is new? In the last 50 years, things that we did that were completely natural to our civilization suddenly approached the global scale. We are affecting the planet as a whole, and as a result, new words that you are now completely familiar with have entered the public discourse in ways they never were before. Global warming, biodiversity, fragmentation of habitats, floods, droughts, wildfires, ozone, air pollution, deforestation, desertification, acidification, glaciers, disappearing Arctic ice, sea level rise. All of these words have entered our public discourse in the last 50 years, because that is the length of time in which our impact on the planet became manifestly global. Now, it isn't only the climate change issue. The great biologist D.O. Wilson has stated that perhaps the greatest tragedy of all will be the loss of species, perhaps as many as half in the next 50 years, and that this may take us much longer to cure than climate warming, and this is due largely to our destruction of the habitats in which these creatures all live. So now I will come briefly to the challenge of sustainability. If you look at UN population predictions, you will find that the population of the Earth is scheduled to level off at mid-century at about 9 billion people. Yes, the rate of growth of population is slowing around the world. In advanced countries, it's already happening, and it will happen in underdeveloped countries. There is a demographic transition in progress, but in order to accomplish that transition, we're going to have to feed, house, clothe, educate, and employ half as many people as presently inhabit the Earth. And demographers understand that the leveling off of population growth has something to do with the increased prosperity of these societies, the movement of people off the farm, the education of women, and so forth. Problem. In the last 50 years, there were serious and very welcome advances in human welfare in most places around the world. But this came at the cost of a greatly increased compromise of our environment and resource depletion. So that leaves us with this critical question, unanswered question, about sustainability of our civilization. Now, as a physicist, I might have phrased the question this way. In the complex interaction between society and nature, is there a stable equilibrium, a stable point? And are the approaches to that stable equilibrium smooth or highly fluctuating? And how many of them are there? But I'd rather phrase the question in the human terms that I have here. Can we sustain a stable society and a stable environment at the same time? And the reason is that we are actors in this drama, and the choices that we make affect the outcome. The whole question of sustainability also started to emerge in the last 50 years when our impact on the globe became manifest. It started perhaps with books like The Silent Spring, The Club of Rome, The Limits to Growth, the great Gro Brundtland report. Or perhaps it started with the first image of the Earth from space, in which we saw that we were all inhabiting a finite planet, blue and alive in the black immensity of space. Whatever the situation, whether we arrive at a stable society and nature, a stable situation, or not, it's clear that there will be a bottleneck at mid-century. That will be the time of maximum population. It may decline after that. We will not have learned as well as we will after that how to cope with the problems. And so there will be a bottleneck at mid-century, and many people predict that. So the choices that we make in the next 50 years actually will determine what kind of society, what sort of environment, how many species we will go into the future with. And what we do now, the decisions that we make now, prepare our children for the difficult decisions ahead. Now, if you look at these names of these books written by some very smart people to celebrate the turning of the millennium, you will see that some exceptionally intelligent thinkers on this matter do not believe that the outcome is assured. The end of nature, the future of life, collapse, our final hour. It is not clear whether we're going to get through this sustainability transition. Now what I'd like to do, and as a result of these concerns, we recently have seen in the last year a sea change in public perceptions and opinion. And we have moved from a question of analysis, a diagnosis of what's going on, to a question of what is the cure? What do you prescribe? Where are the solutions? And we in the universities have no choice but to respond. This is why we have an Environment and Sustainability Initiative at UCSD, and they are being created at universities around the world. The question, will the universities and others create intellectual capital that we need? Will we invent the technologies? Will we educate sustainability professionals? Do we understand how to promote the social changes that are needed? Will we in the universities actually partner with our communities, industry, and government in ways that we haven't before? Will we lead by our own example and have green campuses? And the C.P. Snow question. Will we overcome our own cultural and social barriers? And then there's the Charlie Kennel question. Will we do all these things fast enough? 50 years. So let me tell you a little bit about the intellectual capital that has been created by the subject that I have worked with in the last 15 years, which has been given the name of Earth System Science. And you may think of Scripps Oceanography as purely interested in the ocean, but in fact, it is one of the most complete Earth System Science organizations in the entire world. You used to think of Earth science as dealing with millions and billions of years ago, but as soon as the climate problem became manifest, the Earth Sciences, about 25 years ago, organized a new discipline, Earth System Science, whose job it is to to understand the Earth as it is today and to try to predict what will happen to this Earth over the next 100 years. This meant that we couldn't pursue our academic interests in a single disciplinary, single string approach, but we had to look at the Earth as a complex interacting system of components. And here is the famous diagram that was developed under NASA's leadership about 1986 that shows that if you're interested in the last 100 years, the next 100 years, then you have to couple marine biochemistry and terrestrial ecosystems and ocean dynamics and the atmosphere and tropospheric chemistry, and you have to understand them all as an interacting network. Multidisciplinary science. And by doing this, you also create the scientific basis by which you can understand more local subjects like the environment and ecologies, which are very highly endemic and localized. And it gave the earth sciences a new observing agenda, a new thing to observe. And I'll come to that. So in its first 15 years or so, we worried about basically how the living creatures in the ocean and in our forests interact with the atmosphere. We've worried about how the changes in the atmosphere are occurring, atmospheric composition in particular, greenhouse gases. We worry about the natural cycles of the climate, like the El Nino, and how to sort those out from the human impacts. We worry about natural cycles that might take as much as a century or 1,000 years. And above all, we understand that we can't answer those first four questions without understanding the human dimensions, because the state of nature is gone and we live in an entirely human-dominated environment. But Earth system science called forth a new observing agenda, a new conception of how to observe the Earth. You had to use satellites, because they were the only ones that saw the Earth as a whole, that saw all its systems simultaneously, looked in on the ecologies of every country from the same basis. And by the year 2000, we had created a golden age of Earth observations. Here are some of the satellites that I was privileged to work with at NASA. JASON measures the circulation of the ocean. Landsat measures the forests. Aqua measures the circulation of water in the atmosphere. SAGE measures the sunlight coming from the sun. TRMM is the first satellite to measure rainfall on a global basis. Right now, these satellites are delivering data at an unprecedented rate, and we are in a golden age of Earth observations from space. I am sorry to tell you that over the last, and in the year 2000, these satellites comprised 50% of the global capacity to observe the Earth from space. Over the last 8 years, this program has declined, many of these spacecraft reaching the end of their lives, and it is certainly the case that we can look forward to perhaps a 75% reduction in the capability that the United States deploys for observing the Earth from space at a time when it's never been more critical. Paradoxically, at the same time, the United States also led, with France, the development of an international treaty to create a global Earth observing system of systems in which the nations of the world would pool their observing capacity and information into a common pool so that we could try to understand the Earth as a whole and as an interacting system of systems. This was started by an Earth observation summit attended by ministers of state and opened by Colin Powell in 2003, and I'm sort of sitting in the second to back row there. It was a wonderful event to see. 66 nations 2 years later signed a treaty agreeing to do this. Now, the nations signed the treaty not because they wanted to continue the development of Earth system science, which generated largely this observing capacity. It is because this system is dedicated to the things that will be important to sustainability, which are listed above. These are the 9 goals. Now, you may say, well, this is a political agenda, and so the politicians decided on these goals, and it doesn't really change anything. But if you really believe that that's the purpose of the system, and I do, then it changes everything for our science and makes us ask the question, how can our science fulfill our obligation to sustainability? And how can a system that was designed for science also serve sustainability goals? And that will be the topic of the remaining part of this talk. So where do we go from here? This is the question we scientists have to ask. So let's start first with the technical basis of all the research that we're doing. The observing systems, spacecraft, the platforms, the networks of observing observations in the ocean and on the ground, all the information technology that supports it. And we have to say that the purpose now of deploying all of this technology is not only to increase our understanding of the science, but to proceed from understanding to decision support, to help all the people who need this information to make decisions that will benefit sustainability. This goes beyond assessment, goes beyond diagnosis, and it goes into the area of prescription and cure. Solutions are what's required. So let's look at the situation today. The international treaty covers all of the observing capacity of the contemporary Earth. The spacecraft, aircraft, UAVs, moorings, floats, every kind of active sensor, networks of sensors, and observing land, sea, ice, and air. I'm pleased to tell you that Scripps may be the only organization outside of national laboratories that pursues every aspect of this system in one part or another of its work. A great milestone was just recently celebrated, and this will give you an idea of what a 21st century sensor net actually looks like. This is Project ARGO, and it recently completed its goal of, with international sponsorship, of deploying 3,000 of these little floats that you see off there on the right, invented by Russ Davis in 1988. The floats do the same things that the fish do. They fill and empty their bladders with air. They can go up and down in depth, and they're the first ability that we've had to get high-resolution measurements of ocean circulation, temperature, salinity, and other chemical properties at depth. 3,000 little robots wandering the Earth's ocean, a 21st century system. They stay down for 2 weeks. 1 week, they go up to the surface, they radiate their information to a satellite, 21st century, go back down again, and then the data analysts get busy trying to figure out how the ocean is circulating, and most importantly, where the heat from global warming has gone into the oceans. That's just one example. There are many others. The multi-sensor networks of today are fairly expensive, and the sensors themselves are fairly large. But we can look forward to an entirely new generation of sensors that we actually have it today. Every time you take a picture with your cell phone, if you were to do an environmentally meaningful picture with that cell phone, you'd be part of a sensor net. And we can look forward to the miniaturization of our instruments. You see this, the next generation of ARGO floats and so forth are there on the right. And you can finally find a time when they'll be this small, and they'll be every place in the environment, and there'll be literally hundreds of millions of them that are deployable. And they will be covered from above by satellites and aircraft that tie all of these point measurements together. So given that, then it's clear that the frontier of this particular part of our subject is moving beyond the sensor nets and the platforms. They are just part of an information system, cyber infrastructure, computing, communications, modeling, visualization, and more. And once again, I'm pleased to tell you that Scripps and UCSD are doing exceptionally well. One of the biggest issues, of course, is just sheer raw computing capacity. And so I've drawn 4 of the largest computer systems of the world and one that's about to be built. And you'll notice that the 3 on the diagonal, at San Diego, at Columbia, at NASA, and Lawrence Livermore, are all in the state of California. We have access to the best computational capacity to handle this data. That isn't really, that's necessary but not sufficient. What's even more important is to get the large research organizations of the country working together on large volumes of computational data and observational data. And I'm pleased to say that Scripps, and in partnership with Cal IT2 here on the campus, is participating in the National Lambda Rail Network. At the end of the dot-com boom, many of the companies had overinvested in communications technology. The NSF has bought it up on pennies on the dollar, and we now have an exceptionally high capacity network that will allow very large amounts of data to be simultaneously dealt with by the large research laboratories around the country. And this will mean eventually, as this becomes standard practice, that instead of Scripps or Berkeley, there will be large consortia working simultaneously on the data, using each other's program with middleware that's being worked on right now by Cal IT2, and a whole new scale of collaboration. On my watch, we saw the beginning of it. A demonstration computer line using the Lambda Rail network that connected 2 of my favorite places, the Goddard Space Flight Center and Scripps, working together, visualizing, talking about the same data set. They do this in the oil companies. And soon this technique, I think, will move throughout at least the big laboratories in Earth system science. And this will begin to develop peer-to-peer interactions in which the ideas flow back and forth within the network and are not guided in any central way. As the internet teaches us, a very effective way of collaboration. And many unexpected things come when you start to do that. So you can see then that if you project forward, say, the next 10 years, that there will be a very large and integrated capability of a global regional scale that could do the job. And so, but the purpose of it all, and why we do science even in this area, is to go beyond the information and the understanding and really to start working on decision support. And when we do that, that is when our science is turned into a sustainability science. And it is at this level, that the natural and social sciences become connected to promote adaptive management. So, what kind of decision support have we been involved with already? The community has developed a significant amount of it. For example, down here you see the 2007 IPCC report, in which 20 Scripps scientists and 400 around the world participated, and they all got 1/400th of a Nobel Prize for their efforts. But it was an amazingly successful report. There's the new Stern Review on the economic impacts. There's the Arctic Climate Assessment. And there's one that Scripps itself led, which was our Changing Climate, the first regional assessment of the impacts of local climate change on things that Californians care about. And it was that report that the preamble to Mr. Blair and Mr. Schwarzenegger's agreement lists the reasons why Californians should be concerned, and it came from our report. Here are some lists of it. It looked at the 3 different ranges of warming that you might expect over the next 100 years, and it considers what will happen to the Sierra snowpack, how much sea level rise we'll get, so on and so forth, at the still unknown levels at which climate change may proceed. It's our choice where we want to fall on this diagram at the present time. It's had tremendous impact, largely because of a very simple result. When the temperature goes up, in the Sierra Nevada, the snow line goes up. And more water falling from the sky falls during the winter in heavy rains, and less is stored in the Sierra Nevada snowpack. There's more water stored in that snowpack until spring than exists in the entire California Water Project. Recently, Scripps scientist Tim Barnett made a prediction that suggests that under progressive temperature increase, situations like this can become irreversible. And he has predicted that the snowpack in the Rocky Mountains will disappear by the year 2040. And so we depend on the Rocky Mountains, and we depend on the Sierra Nevada for much of our water, and its timing and nature will change, and our water management practices will have to do so if we're going to cope with this. The problem is even more severe in Asia, where 1/6 of the world's population is affected by the great rivers of Asia, the Yangtze, the Brahmaputra, the Indus, the Ganges. All of these rivers derive their water from the mountain snows in the Himalayas, and 2 billion people depend on it. So this was a highly impactful impact study. We even have had some experience at the University of California elsewhere in decision support, specific programs that take the knowledge that science has been generated and communicate it in terms that people can understand to the people that need it. We've done it. Agricultural extension, California Cooperative Fisheries Investigation led by Scripps for the last 60 years. But now we need decision support for all the elements of sustainability. But we can begin to see from things that we've already done what will be required. Now there are new frontiers of assessments, trying to figure out what will happen and communicating that to the people that need it. One of the most important ones actually is economics, general economics. Most people understand that the markets are at least as important as government action in conditioning how our world will behave. But in order to have an impact on the people who think about the markets, the reinsurance companies, Wall Street, the banks, venture capital, and so forth, these regional assessments, which were made at the current level of capability for 100-year projections, need to be reduced to investment timescales. We need to be able to predict what we can do, what will happen in the next 10 years, next 15 years, and we need to say where it will happen with greater specificity. Will it affect the Central Valley? Will it affect the Sierra Nevada? So there's a whole new frontier of assessments and measurements and knowledge generation that will be needed to appeal to the markets. But I think people are beginning to think about it. And then finally, there's local environmental decision support, where you and I live. Everybody lives in a locality. We don't live on the globe. We live in San Diego. The globe is out there. If you look at each picture in this inset, it is a different environmental region in the state of California. This is how diverse our state is, and how articulated our understanding of Earth system science and environmental and ecological sciences will have to be in order to really affect people who manage these, who think about the health of these very diverse ecological regions within the state. There are 16 climatic regions within the state of California. And it's at the local level that we encounter the greatest difficulty. In fact, all sustainability is local because all important decisions are made in a local context. In fact, the most important question in environmental science is not what's going to happen to the globe, it's what's going to happen to me, to my family, to our children. That's the most important question. But in each of our regions is unique. We have our own ways of making decisions. So the decision support has to tailor to the decision makers. At the present time, all of these social, economic, political, legal, cultural forces overcome the technical excellence that can be deployed in decision support. People who are generating information, people who make the decision, don't talk to one another. Not enough of what we know is being used regionally and locally. The science has become disconnected from economics and politics. Our public communications scientists is obscure. And the net result of this concatenation of results is that decision processes in the environmental sciences in particular are dangerously long and complex. There was a plan to remediate the danger to New Orleans from hurricanes. That plan was 30 years in development and review. We can no longer afford dangerously long and complex decision processes when each generation will face and have a different climate. So what do we need to do? Think globally. Assess regionally, figure out what's going to happen to the things, natural systems in our own region, and act locally. And it is here where this sustainability informatics that I've begun to talk about may ultimately play a role. Because what I think we are seeing in the world of research is a convergence of earth science and biology and social science that is being enabled and supported by our ability to manage information. And the goal of all of this has, at some point in the future, to make us continuously aware of the state of the Earth and its systems and how we interact with it. And it's that continuous awareness that we need to manage a sustainable use of resources and the environment. And of course, because it will be globally distributed, it will promote much more coordinated responses across the globe. Now, there are many proposals that you're beginning to hear about. Maybe we should begin to take major steps to alter our global environment. Should we fertilize the oceans to make the planktons grow on a huge scale? Should we put aerosols in the upper atmosphere to reflect some of the sunlight back into space so it doesn't warm us as much? Should we do these big things? And I ask you the question, do we dare undertake any of these geoengineering projects until we've got continuous awareness of how our system is acting so that we can assess these projects before scale up? So what are we talking about? Trying to create sustainability informatics. It's an intergenerational project. It will take 50 years to create or more. Unfortunately, we need it in 50 years. Now, the scientific community has been used to undertaking projects that are intergenerational, whether it is solar system exploration, physics and cosmology, the Large Hadron Collider is there, the Webb Space Telescope, controlled thermonuclear fusion, new experiment is just starting, the genome, Keeling, and the climate science. The reason these projects came to fruition with all of the fluctuations in government policy and changes in leadership, evolving technological approaches, with all that changes over a couple of generations that it takes to do these projects were stabilized by the stability of scientific goals and scientific questions. The scientists kept coming back over and over and over again, asking the same question and demanding the projects to answer them. Administration after administration, country after country. That's how the scientists got these intergenerational projects done. Now, sustainability, informatics on sustainability itself is clearly intergenerational. But where will the stability of goals come from? Will it come from the science alone? Unlikely. It's the largest single project taking care of the Earth that we've ever tried, and will ever have to, probably. Where will that stability of goal come from? It will come only if there's a stable set of social goals for the entire world that can then allow the science to come forth and help develop solutions. I don't have any idea how to do this. I have a few guidelines. As we think about building such a system, it ought to self-assemble. We've got to design and think about all of our scientific systems in earth science, assuming the world is complex and changing at all times. And think more like the internet. Look at, this is the map of the gene network of the E. coli bacteria. Pretty damn complicated system. The earth is much more complicated than that. But we really need to think about how the internet self-assembled in order to cope with the complexity of the tasks ahead of us. Another thing, the future, the past is no longer a guide to the future in any of these areas. But it takes 10, 15 years, 20 years to deploy some of these large technologies. How in the world, without any guidance, true guidance from the past, are you going to be able to make the decision even to do the science? And what you must do is use what you've learned and use what you presently know how to predict in order to guess what you will need in the future and start doing it now. We're embarking on that now by thinking about the mitigation of climate change, but it will be true for the systems that we use to diagnose what we do and how the climate is evolving. So you watch the environmental trends, you watch the population trends, and you build a little, watch a little, build a little more. But always think, predict the future. And then finally, and here's the important point, we should engineer decisions, not systems. The information that we use, we should understand the end-to-end decision process. We should understand what we scientists are doing and how it is used in the decision arena and how it should be used and how we should present it. And it's more important to get a timely, good enough decision than it is to build a perfect system. So in doubt, if in doubt, sacrifice design efficiency to decision efficiency. And this is where our collaborations with the social sciences and the humanities are really needed and where it has not occurred. And we can count. Here is where we count the losses that we have suffered because the scientists and the social scientists don't talk together. Dangerously long, complex decisions about the environment that we live in and depend on. So C.P. Snow, where are you when we need you? He was a chemist, he wrote a number of famous novels, and he was an important public servant, Lord Snow. And he made it clear, and I repeat, without socially aware engineering, without environmentally aware management in government and industry, without the public policy and sciences, without the fundamental humanism, then what we do in science and technology at Scripps, at UCSD, and around the world will most assuredly fail because there's not much time. Lord Snow is buried in Christ's College. That's a picture of it where I was. And I borrowed a line from a great poet from the Cambridge poet from the 17th century, Andrew Marvell. The poem was to his coy mistress. I've changed the words a little bit and I address it to my colleagues in the natural and social sciences. Had we world enough and time, this coyness, colleagues, were no crime. And the second line is, we would sit down and think. Had we world enough and time. Thank you. The question is, am I inferring that we are running out of world and that we're running out of time? And my answer is that the human imprint has covered now the entire Earth and is changing the surface of the Earth. And as far as a lot of smart people can tell, we've got about 50 years before this problem becomes its most acute. So we're already changing the globe, and we've got 50 years to try to deal with it. And so I think there's cause for worry. The question is, it sounds like I disagree with Jim Hansen from NASA. His reasoning is somewhat different from mine. Jim Hansen has testified before Congress that he thinks we're about 10 years from some irreversible changes in the climate that we would not be able to get back through the mitigation steps. There would be things like the disappearance of all the ice or the snows in major mountain regions and various other things. And he has said 10 years. Hansen is one of our most distinguished climate scientists. He's always been on the far edge of these predictions, but he has not yet been proven wrong. And I think you have to listen to him with great care. I did not look at the technical issue. Are there turning points, tipping points in the climate system that our Earth system model doesn't predict? I looked at just the question, when will the human pressure on the environment be the greatest? And that's 50 years from now. Some of these things may happen before that. So the question of tipping points is a rather delicate one. Right now, for example, people are worried that the ice caps, the land ice, particularly in Greenland and now more recently in Antarctica, is disintegrating, not melting slowly, but disintegrating a lot faster than we thought. And this may lead to a more rapid sea level rise than we thought. That is a kind of tipping point. The disappearance of the sea ice in the Arctic will probably take place by mid-century. Now, this is a result, actually, that was discovered by some work that actually Walter Munk played a role in bringing to light. Many years ago, when we did things like launch ballistic missiles through the sea ice, the U.S. sent submarines underneath the sea ice. And they were very interested in finding the thin spots in the ice. So they were measuring the thickness of the ice with great detail since about the 1970s. And finally, when some of that information was declassified, it appeared that the thickness of the sea ice was declining by about 10% a decade. 10% a decade, which meant, if you extrapolate, that by 50 years from now, it would be gone. And the satellites now observing the extent of the sea ice in September, which is their fiducial point, also now reach the same conclusion. So many years ago, the U.S. Navy already concluded that the sea ice was going to disappear over the next 50 years. That's an irreversible change. Now this one may not be all bad. Fort Churchill in Manitoba, which was a port that ships grain to Europe and was usually open for 3 months during the summer, is now open for 6 months, and the Canadians are actually building more port facilities because they will be able to ship directly across the Arctic. And that will probably help the carbon footprint of the shipping industry, which is alarmingly large. It's not all bad, but that is another irreversible. That is a change that would remain irreversible so long as the temperature continues to increase monotonically. And so there are tipping points. We know, for example, that our present climate models do not predict retrospectively the very rapid changes in atmospheric temperature that have been inferred from the ice core measurements that Jeff Severinghaus and others around the world, and Jeff Severinghaus at Scripps, have seen 5 and 10 year rapid increases of 5 degrees in atmospheric temperature. And our models don't predict anything that labile. They have too many gaps in them. They're not good enough to do that. So yes, there are rapid things that our models, our computer models, which look incrementally into the future aren't predicting. So there's always this question of a tipping point. Now, a physicist would call a tipping point a phase change, when you change liquid water to ice. And physicists also know that when there is a phase change about to occur, there's a very high level of fluctuations in the system that you can detect. You know you're right on the verge of something if you can see those fluctuations. So that's another argument for continuous awareness. Are we going to be able to detect the increased fluctuations that would precede some major and dangerous change in the climate? I have no idea, but I would not go forward into the long future without having the assurance of building a continuous awareness system. The question is that in the last 8 years, not only the satellite system, but other funding for this kind of science seems to have declined. And how would I address that issue? And I think the impact of budget declines has been greatest in the scientific satellite area. And it's really been the fact that a proposal to extend climate measurements on a large multi-agency national weather system has failed, and there have been no plans to replace it. And so I think the Earth observations from space are a singular case. Now, our colleague Ramanathan, whom I think you've heard speak, he of the atmospheric brown cloud fame, Ram was chairman of the National Academy Committee this year that reviewed the progress of the U.S. climate science program. And I'm going to make stronger statements than his report actually did. And the overall funding for climate science has only slowly declined. For the satellites, it's been precipitous. There's been a lack of planning and lead development. But what really happened was that because, this is my interpretation, because there was a great deal of doubt at high levels in the government that many of these projections were true, there was an unwillingness to fund and support those kinds of activities, the decision support activities, that would make the fairly good climate science that did occur during the last 8 years, make it relevant to policy and to decision making. So there was an underfunding of the social sciences aspect of this program in particular. One of the things that we did here in California that did not occur throughout the country as a result of federal initiative was to have regional climate impact assessments. Regional assessments bring the story of climate change home to the people. And there was a sense at high levels, again, that since the global situation was so insecure, that if we went to the more chancy regional predictions, then we would just be exciting people for no really solid reason. So there was two things that happened. That there wasn't a federal, or for that matter, a truly international commitment to regional projections done by the regions themselves. Although in the event, New England, the central plain states, and California did their own assessments anyhow, because they wanted to. But the frustration of a coherent program of regional assessments and the complete underfunding of the social science of this meant that a lot of the good science that was being generated could not find a way into the decision arena. How do I feel about the outcome of the Intergovernmental Panel on Climate Change? As you know, this is a worldwide panel involving thousands of scientists from every country. There were 3 working groups. Working group 1 was on the physical science of the climate, why it is changing and how much and how fast. The second one was on best guesstimates on the impacts on water resources, agriculture, forestry, and so forth. And the third was an assessment of what we might do to mitigate our emissions of greenhouse gases. Working Group 1 came out, and it's very interesting. Working Group 1 is the oldest one. And this climate panel has been in existence with different membership, of course, since 1988. In 1990, they came out with a first summary statement, which was, this is climate science, and this is what it is. It was just a description of what we do to analyze the climate. In their second report, they said in their summary statement about the attribution question, are human beings involved in the change in climate? The second report said, well, it's a very plausible hypothesis, but right now we do not see the evidence. There's not a clear balance of evidence. The third report, 7 years later, said it's more likely than not that human beings are involved in the climate. And this report in 2007 said that the human interaction with the climate and the changes that are occurring are unequivocally due to human interaction. And 3 months later, that report was the one that attracted the most attention. It's the most developed, and the science is the best, and it really follows from Earth system science as I described it. The question of the impacts on ecosystems, on agriculture, on water resources, they're much less well developed. But this Working Group 2 came out and said that they see impacts in impacts already in each of the areas that they looked at, and those impacts can be found in every continent. Working Group 3, I haven't studied so well, so I'd rather not comment on it, but it tells you a lot about what you could do and the various means of reducing carbon emissions, and I'm not an expert on that area. Did I interpret the question that at 6 billion, it looks like the question, how do I feel about this proposition that at 6 billion global population, it looks like many of our systems are not in a sustainable situation, so how can we possibly do it when we have 50% more people and probably 4 or 5 times the energy consumption? And the answer is, it's the biggest challenge that the global society ever faced.